Sorry, give me a chance to get back. All right, cool. So, in your mind, just again, let's just do a quick warm up, take a few moments. And you don't have to write out a formal definition of this. What does that mean? It's going to be relevant today, so it's not just like a pointless exercise to think about this again. Okay, yeah, I mean, it looks like we write a formal definition. What does it mean? Set F is closed if there's actually a couple ways you could. Let's write some equivalences. Let's do it together. Somebody give me one. What's one way to discern if a set is closed or not? Is this one? Is that one? True? False? Are sets like doors? That's not true, right? Just because you're not open doesn't mean you're closed. What does mean you're closed? Give me one thing. Anything. I can think of 3. How could we say this in terms of open sets? How could we do it? Trinity, oh, go ahead. You got something better anyway.
Yeah, all of its limit points are contained in the set.
Beautiful. So if F contains all its limit points, what's a limit point? What's a word? We're using words. We're not going to get that granular. What's a limit point? I think this seems like a good warm up for us today. It's okay. It's like karma free too. We say X is a limit point F if what? Look at the phrase. The term limit point. What does that imply? There's a clue in it. Trinity, do you have a sense? You've already helped me, so I don't want to harass you too much, but you might know.
I mean, try not to cheat.
I appreciate that. That's okay. That's all right.
But it's like if within like the neighborhood around it, there's an element of the set within that neighborhood.
Yeah, that's pretty damn close. There's a quantifier issue in there, but that's all. That so we'd say X is a limit point of F if every punctured neighborhood of X intersects F. So you had the right idea, 100%. Cool. What's another way to decide if we have a limit point? I guess today's equivalence day. Anna, what do you think?
I was thinking of a way to say that, but I don't want to like verbally say it.
Say it.
Instead of saying it.
Yeah, say it.
Oh, it was that.
Oh, it was that. Okay. What does it mean to be a limit? What is an essential thing to have before you can even have a limit? Are these questions too out there and abstract?
Yeah, I feel like
what does a limit result from? I'm like totally chilled to just wait. And you can cheat. Why don't we cheat? Not cheating, why don't we freaking look? What is another way to say we have a limit point? Hell, I'll cheat. Let me get my book out. Because if we don't understand these things, what we're going to talk about today might not be as meaningful. So let's just definitely make sure we have these. Okay, so definition 324 is essentially what Trinity gave us. What does theorem 325 say? X is a limit point if, limit point of f, if.
It's if X is like the limit of some sequence that's contained in the set.
Beautiful. It's the limit of a sequence, right? And so the thing I was trying to get for is to have a limit, you have to have a sequence. You have to have something approaching something. Or X is the limit of a sequence in F. And that's key. The sequence of points has to be inside F. So, i.e., let's get more technical. There exists some X sub n sequence contained in F such that X sub n converges to X. Awesome. That's like the other great way to think of it, and it's in the word, right? So remember that, make that correlation. It's literally the limit of a sequence. So F contains all its limit points. That means if I've got a sequence of points converging to some place, like this sequence looks like it's converging somewhere, but it doesn't look like it's converging, and I've made that suggestive, right? That it looks like it's converging to something that's not in that set. So we don't want anything like that. We want every convergent sequence to converge in the set. Contains all of its limit points. What's another way to categorize a closed set? Set F is closed, and how about this? If, what about F complement?
If its complement is open.
Beautiful. So there we can relate open and closed. It's about complements. So if F complement is an open set. Okay. What does it mean to say a set F is bounded?
Would it mean like there's like a limit to it?
Let's be more precise. This is good. Thanks for joining in. I appreciate that. So when you say limit to it, what does that mean? I think I understand what you mean.
Like if it's bounded, then it means like there's a certain space to it rather than like being like infinity. I don't know if that's.
Let's keep going. This is good. Yeah, it's like contained in something,
Yeah,
right?
it's contained.
How do we get more precise? So F is bounded if there is some, what do we usually get when we have boundedness? So Anna, you're absolutely right. Here's a set that's bounded. Make it crazy here. And it's all like that. That set looks bounded. How do I quantify that mathematically? There exists some what? Some bound? Yeah, that's good. Good boy. Did it. How do I say there is some bound mathematically? finish the sentence. Please. So forceful on a Monday. I don't really have anything to offer you besides, goodwill. Yeah, there's nothing good in there to bait you with, to like award you. What does it mean to be bounded? Can we look it up?
Looking at my notes.
Okay, cool, all right.
It's for, so if there's some n greater than 0, all of the elements of the set are less than or equal to n. Well, the absolute value.
Yes, lovely. If thanks. Yes. If there's some big number, it doesn't even have to be a big number. If here's 0 right here, then this m would suffice. Right? Essentially what we're saying is this, that it lives between some number and its opposite. Everything in that set is in some closed interval from minus m to m. All I know is f in here. F lives in here. Okay. All right, so we understand what closed is, we understand what bounded is. The two of these things together amalgamate into a property that's one of the most fundamental properties in real analysis. But it's going to take us a few bits to get there, because our book doesn't present that as the obvious definition. So let's just get it. Let's get our definition out here. Definition: a set K is compact if every sequence in K has a convergent subsequence. That is one way to define this thing called compactness, and we're going to take a look at what other ways, because that's like kind of weird. That doesn't feel good, right? It's just like, it's the minute we start talking about subsequences, things start to get a little on the edge of comfort, for sure. So we need to prove a more fundamental result. And let's see, do I have this? Yes. So this is theorem 3.4. And in the process of proving this theorem, hopefully we'll gain some insight into what the hell does that mean up there. So theorem 3.3.4, we have a set K in the reals, and it is compact. I will abbreviate that often, CPT, you'll see that. I've already spent more time explaining the abbreviation than it will save forever, but hey, what the hell. Is compact if and only if K is closed and bounded. Closed and bounded is the classic characterization. In a lot of books, real analysis books, would present the definition of compactness as this, and then this would be kind of an ancillary way to, wow, I don't think I've ever said ancillary. And that's awesome. Sometimes shit just comes out, you don't know what's happening. Ancillary, and I think I used it right. I don't want to know if I didn't, so that's all right. So let's do a proof of this. Let's go the easy direction. So we're gonna first assume it is closed and bounded. So proof this direction first, assume K is closed and bounded. And I'm gonna really want some help from you all today, bless you. It's either the best day to show up or the worst day to show up for the three of you. So the heat is on. The heat is on, my friends. All right, we're gonna assume K is closed and bounded. We need to show that this other definition holds true. So the first thing I'm gonna do is take a sequence in K. Let this be a sequence in K. So we are going to rack our brains to pull together the proof. And it's actually not this won't be very involved. So we've got K is closed and bounded. The sequence is in K. How can I get a convergent subsequence? Oh, and God, we're gonna add this. Has a convergent subsequence that converges in K. Add this to the definition. That converges in K. That's essential. Sorry, we're gonna miss that. You'll see why in just a second. So I've got a sequence. What are ways to get convergent subsequences once you have a sequence? What are some major results? One in particular. Yes, exactly. What does that theorem say?
Every bounded sequence has a convergent subsequence.
Beautiful, right? So if this is a sequence in K and K is bounded, that means this sequence is bounded then. Does that make sense? Yeah, so we have a sequence in K. Since K is bounded, so is the sequence, because it lives in K. By Bolzano-Weierstrass, there exists in X sub n sub j, I'll use j because we already got K as the set name, a subsequence of that sequence that converges to some x. So we have X sub n sub j converging to x, i.e., I'll just write that out, it's same words, just different notation. What do I need to show? What do we need to show about that x? It's in K, yeah. That limit is actually in K, because that's what it means to be compact for us. So why is that x in K? So why is this x in K? What are we assuming? Which of these two properties? We use boundedness. How do we use closeness? Right now, I don't know that x is in K, so I've got my set here. Here's K. I've got my subsequence converging. Let's make it an edgy thing like that, literally. No pun intended, really, but ended up being that way. So I've got this converging to this x. How do I know that that x is in K? What's another name for this x that we've already seen today? X is a what of K? A what, huh? Yeah, it's a limit point. I got a sequence converging to x, so x is a limit point. This means x is a limit point of K. Diana. So, since K is closed, it contains its limit points. x is an element of k. And we're done. So, well, that's it. That's this direction. Let's get it finished, and then let's just summarize really quick. We assumed the set was closed and bounded. We took a sequence in the set. We produced a subsequence that converges, and we showed that subsequence converges in the set. So we have met that definition up there. We're good. It has come down to the three of us now. They whittle away. Yes. The pressure builds. Yeah. You're gonna go out and pull the fire alarm.
Yeah. Why did I do it?
All right, I'll tell you what though. What we will do so that you two, I mean, we can keep doing this if you want, or we could, you want to keep doing this? Or I could give you time to work on your homework in here. But I want to finish this proof.
Yeah.
We're going to do this proof, and then you two are going to work on homework? You don't care? Whichever way? Okay, great. Great. I hate to like just waste a day.
Yeah.
I just feel like we can. Okay, so now we're going to go the other way. And this one's a little trickier. So now, this direction. So we're going to assume K is compact in that sense up there. Every sequence in K has a convergent subsequence in K. So assume K is compact. We need to show, let's put our shining star goal up here. Need to show two things. K is bounded, and then K is closed. So, one of these is actually pretty straightforward, but the boundedness one is tricky. So let's first show that K is bounded. Proof that K must be bounded. And the way to do this is to assume it's not bounded. And show that blows the compactness. So assume K is not bounded. So we're going to wind up with a contradiction here, contradicting the assumption of compactness. So what this means is now K is not bounded. So let me put up, this is going to be slightly misleading, but let's say, K is like this set here. I don't know what K looks like, but it's maybe like the interval from 1 to infinity or something like that. Let's just say that. All I know is it doesn't fit in some nice little minus m to m window. There's no window like this that I can put the whole set inside. So, since it's bounded, unbounded, thus, and we're going to build a sequence of points that can't have a convergent subsequence because of this unboundedness. Thus, we can choose an x1 in K such that the magnitude of x1 is bigger than 1. Why is that? Why do I know I can do that? What would it mean if I couldn't do that? Which is really the way to answer my question. What would it mean if I couldn't find an x1 whose magnitude was bigger than 1? Wow.
1 would be the bound.
Yeah, exactly. 1 would be an upper bound, right? So since this thing is unbounded, this has to be possible. So I can definitely pick this x sub 1 in here. I can similarly, I can pick an x sub 2 in K whose magnitude is bigger than 2. By the same reason you just gave, Ashley, right? So if I couldn't do this, 2 would be an upper bound on the magnitudes. And it's not, because that would mean it was bounded. So we can continue on with this. We can choose an x sub j in K such that the magnitude of x sub j is bigger than j. Because if I couldn't, it must have been bounded, and I lied. But we don't lie in math. We try not to lie. So we've got this sequence now of points, and I'm abusing this. They could be negative and bouncing back and forth and expanding out, but the key thing is they are growing out toward the ends of the real number line. Right? And each one is further away from 0 than the previous one. There's no implication of monotonicity here. This x1 could actually be bigger than this one. I'm not saying it isn't. I mean, I could have made this x1. That would have been true. It's all good. There's no order implied here. But I do now have this sequence. So x sub n is a sequence in K. It's an unbounded sequence in K. Could I have a convergent subsequence in here? So I'm going to write a sentence, and I want one of you two to help me out here. There can be no convergent subsequence. X sub n sub j. Because why? Let me help here a little bit. First off, I know that the magnitude of x sub n sub j is bigger than n sub j. We built the sequence to be that way. It's always bigger than its index, or its magnitude is bigger than its index. And every convergent sequence is what? What word finishes this and gets to the heart of why this can't happen? What's that?
Is it bounded?
Yeah, exactly. And every convergent sequence is bounded. Yep, exactly. And every convergent sequence is bounded. Thus, an unbounded sequence can't be convergent. Nice. Cool. So this contradicts the assumption that it is compact, because we picked a sequence in there, we picked a very specific one, but in a compact set, every sequence, no matter how you pick it, has a convergent subsequence. So this contradicts the assumption of compactness. I'm going to put a star and get us back. This is the one. I don't want to have to write it. All right, so we have shown if a set is compact according to that definition, it must be bounded. Now we got to show it's closed. Proof that K is closed. How do I show a set is closed? It's like Groundhog's Day in here, isn't it? One of the best movies, by the way, ever made, inarguably. That's right, right?
That's fair.
Okay, cool. I'm glad we agree on that. How do I show set is closed? How long ago was it that that was? What's that? Limit points. Yeah. Limit points. Yes. The limit points thing. So, to show this, let x sub n be a sequence in K converging to a point X. I don't know where X is, I have to show that it's in K. How can we get there? So now I've got a sequence converging to a point. How can I get from the only thing I can work with, that top definition, how can I get this point into K? Kind of it's almost a two-step process. I'll write up some things here. So we've got X and X. So look at that definition of compactness. So I've got a sequence. I've got the sequence in K. I know it converges to X, but from compactness, I know it has a subsequence that converges to a thing in K as well. So let's write that out. By the assumption of compactness, compactness, we know there exists a subsequence such that x sub n sub j converges in K, to a point in K. How do I know that that point is this x?
All subsequences of a convergent sequence converge to the same value as
Thank you. Yes. If I have a convergent sequence, every subsequence goes to the same place. So if this goes to x, the original sequence, then this subsequence must converge to x as well. And by the assumption of compactness, that must be in K. Since every subsequence of a convergent sequence converges in K, or converges to the same point, we know that x must be in K. Cool. Did we show everything that I think we did? Well, let's take a look at some examples. All right, so 3, 3 here. Okay, yeah, let's do a little work together. So let's take a look at some sets, and I honestly think this might help with your current homework as well, because it's basically the same problems except asking about compactness. So this is, let's do a couple exercises together. So this is 331. Show if K is compact and non-empty, then soup K and inf K exist and are elements of K. Take a minute. Can you pull together a proof of this? Let's just take our time and think. Just checking my email real quick. I'm not like just gonna go check the news or anything. Let's just work with soup, you know? Just one thing at a time. Just soup to start off with. When does a soup exist? What does the axiom of completeness say? Yeah, that's the answer, right? Yeah. Yeah, what you thinking?
Well, I was just finding the definition of like soup, like.
Awesome,
all
cool.
classes. It's if, for all epsilon greater than 0, there's some element of the set, where the soup minus epsilon is less than that element.
Nice, so you're pulling out lemma 138.
Yes.
Absolutely gonna be super important for one of these, for sure. So let's pull that up here. Lemma 138 says that if S equals soup of K, let's put everything in terms of K, then for all epsilon greater than 0, there exists some X in K such that S minus epsilon is less than X. Yeah, exactly. And if this is my soup and I go a little bit to the left, I can always find some element of the set inside there. Because if I couldn't, then this isn't even an upper bound on the set. All right, what else do we know about, so like there's even a more fundamental result. When does the soup exist? So every, what's that? Yeah, bounded, right, yeah, absolutely. So A soup exists because, why do I know K is bounded? Yes, thank you. Beautiful, yes. K is compact, so we know that's equivalent to closed and bounded. So because K is compact, hence bounded, and then therefore this follows from the axiom of completeness that every bounded real collection has a least upper bound. That if you're bounded, you have a least upper bound. Cool. So we used that. Now we can go to this. Why is the soup in K? So what have we used? We've used boundedness here. What's the other property of compactness that we probably want to kick in here? Closeness. So how can I pull this all together? Let's just loosely, yeah. How can we pull this all together? We've got closeness. So the answer is going to be here because it's closed, but that doesn't get to the details. Can I produce a sequence converging to the soup? Do we even have a result that maybe says that somewhere? I feel like we might. Let's take a look here. Because if you have a soup, you certainly can use lemma 138 to get a sequence that converges there. Just keep picking epsilon smaller and smaller. I feel like we have that result somewhere. But I don't know exactly where it is. Screw it, we'll just prove it ourselves. We don't need to look it up. So look, we got lemma 138 here. So if I let epsilon be 1 over n, and I look at s minus 1 over n, for each n, I can find an x sub n inside that little window that's in the set. So, because, let's do this. Step 1 is get a sequence converging to soup K. So to do this, we're going to use lemma 138 with epsilon equals 1 over n. For each n, we can find an x sub n such that soup minus 1 over n is less than x sub n, and this x sub n in the set K, more particularly. I can find some element of the set K, and then that's going to have to be less than or equal to s. So that's from lemma 138. Thus, this sequence x sub n converges to the soup. Does that sound right? Make sure that you believe that. It's kind of the picture helps. So I have a sequence in K converging to the soup of K. Why do I know soup of K is in K? What haven't we used? What is our assumption? That we're compact. We used boundedness already. How do we use closedness? It's a limit point, exactly. I've just shown, I produced a sequence that, thank you Ashley, I produced a sequence that converges to the soup. That means it's a limit point, and since K is closed, it contains all its limit points. And since K is closed, that's quite, its blank might not be quite long enough, it contains all its limit points, i.e. there. All right. Okay, so that's like proof time. Now we're gonna do a couple without proof. This is just like looking at the sets and you tell me, are these compact? So yeah, I think in section 3.1 you've got this problem and where they ask, are these sets open or closed? I don't quite remember exactly, but in oh yeah, 3.2.3, that problem. So we have the companion for that. Compact or not? Let me pop a couple up here. I gotta run to the restroom, so pretty classic move on my part. Dump a bunch of shit in front of you, run away. Be right back, friends. Let's just start with those three. Can't believe we only meet 9 more times after today. What's that? That's it, isn't that crazy? Guess what? It is horrifying. Maybe we should all just keep meeting through the summer. That's a good look up, then perfectly timed look up, yeah. What about N? The naturals, is this compact? Why you say no? Beautiful. It's that simple. Is it closed? Because I totally agree with you on the not bounded. Is it closed? I mean, that's enough to blow it, right? It's got to be both to be compact. So it's not bounded. Is it closed? Here's an easy way to see it, maybe. What is its complement? What is the complement? Ooh, that's the wrong way. What is the complement of N? It's everything except, you know, this nice, let's see, except 1, 2, 3. Is that open? Just pluck out these. Pluck out the naturals. Is that an open set? Complement is open. Just a quick reason. Does that make sense that it is? Because if say you take a point that's in here, you can always find a little open neighborhood around any of those points that's contained in that complement. So I think in some ways that's the easiest way to see that it is definitely closed. So it is not bounded, but it is closed. Doesn't matter, it's not compact. What about the next? We only have two things to check, right? Closed and bounded. It's bounded, right? For sure, we got that. It literally lives in this closed interval. So this is bounded. Cool. Check. Closed. Is there a sequence in there that doesn't converge in there? You find a sequence of points in this crazy ass fuzzy construction that doesn't converge in there. Is there an irrational number in that interval? No. Is this an irrational number? Yeah. That lives in there. Can I find a sequence of rationals converging to this? Yes, why? Give me a sequence converging to this.
0.7, 0.70, 0.7.
Thank you. Yes, that's it. Once you own the decimal expansion, you own a sequence. Yeah? So I can definitely find a sequence converging to non-rational things in here. So this is not closed. It's got lots of holes. I mean, it's got a hell of a lot of holes in it. An uncountable number of holes in it. So it is not closed. So it can't be compact. I don't need to like present what's next. You can look at the list. You've seen that waiting for us. Cantor set compact. Let's see if I can point you. Certain. Is it bounded? Is Cantor set bounded? Unbounded? Let's try to find some facts about the Cantor set here. Oh shit! Well, I think they're nicely. Bless you. Can you think of that? Just think of the construction of the Cantors. How does that work? And as mathematicians, this is something you should definitely know. You might not know now, but after this, you will clearly remember it. How do I build a Cantor set?
So you continuously take out the
Middle thirds, right? It's all about middle thirds. So Cantor set is a sequence of sets. That's how we think about it. Here's the first one. Second one, remove the middle third. Remove the middle third. Yeah, is it bounded? Yeah, right, it lives in the open interval 0 to 1. I mean, if this was bounded, this sure the hell is bounded. Yeah, so it's definitely bounded. Let's talk one more time about how you build it. So it was the sequence of sets, C0, C1, remove that middle third, C2, remove those middle thirds, on down, and we said the Cantor set was the intersection of all of those. at any particular stage, are these sets closed? Is this closed? The closed interval 0 to 1? Yeah, right, yeah. Are these closed, each one? Yeah, they got their endpoints, right? I mean, your ideas of closedness are still okay. Closed intervals, they're closed. So this shit's all closed. And the camera set is the intersection of all of those. I'd like you to take a look at property, or theorem 3214 on page 92. When you get there, because I was hoping we get there kind of the way we got there today. Theorem 3214 says, part 2 says the intersection of an arbitrary collection of closed sets is closed. So this must be closed. So the Cantor set is compact. And I think we're going to stop there for today, because the next thing I want to talk about is a much heavier way to think about compactness, and I want us all to be here. So, and you two have carried the burden for everyone. You who aren't here today, here's who carried the burden. You can send them cards and flowers. So how about maybe just work, if you want to work on the homework, let's hang out here a little bit, use our time together. Does that sound okay?